I really appreciate the opportunity to talk today. I do apologize. We were originally scheduled for last week, and due to some personal issues, we moved it back a week, and also in recognition for Martin Luther King Day. Today, we're going to discuss the 24 dual flow plates with the BioFlux. I'm going to start out with a brief overview of Fluxion Biosciences, the basic principles of the BioFlux itself, some important parameters for live cell assays, and then go into more detail about what the BioFlux can do and some of the applications that we have for our system. The origins of the BioFlux start out in the UC Berkeley, where our CTO, Christian Ionescu Zanetti, was a postdoc, and he wanted to use microfluidic technology to address unmet and underserved research needs. The initial and what he eventually developed, or the company eventually developed, was the most advanced automated patch clamping system for electrophysiologists. But in the process, the BioFlux was the first to market using the same microfluidic technology that enhanced cell-based assays. The IsoFlux built on the experience from both of these products and created what is today the most sensitive system for collecting and recovering circulating tumor cells. So a little bit about the company. It was founded in 2005, backed by leading VC firms. We have over 200 BioFlux instruments in the world. Just installed our first one in Malaysia about 2.5 weeks ago. Starting out, we had 5 NIH SBIR awards, and we've been awarded the R&D 100 for being the most significant, one of the most significant products that came out for all 3 of our systems. The products that we have include the BioFlux system for physiologically relevant cell-based assays, the IonFlux system for automated patch clamping, which is now sold through molecular devices, and the IsoFlux system for isolation of circulating tumor cells. This is a partial customer list that was put together a couple of years ago. The BioFlux was launched in 2008, and one of the most gratifying things that I found in my job is going into laboratories where customers have not only used the technology, but have developed assays that the BioFlux is an integral and independent part of, where entire research programs, R01 grants, and then furthermore, graduate students and research has been dependent, and BioFlux has been very useful for. To date, we've had several graduate students finish their master's thesis and doctoral dissertations using the BioFlux system. A couple critical variables for live cell analysis include things like shear stress. Shear is something that is relatively new in the area of cell biology, and it's the importance of maintaining a consistent mechanical force over top of tissue and this or cells, which comes into place for why the BioFlux provides a more physiologically relevant condition. The continual flow of material that comes through the BioFlux channels enables the stability of the culturing conditions. And by doing so, the assay reliability and reproducibility is increased. And then, in addition to that, the technology of the BioFlux allows for time-lapse imaging to take real-time data instead of just endpoint data. 2 early adapters of the BioFlux include platelets and biofilms. On the left, you have a video of Pseudomonas, which is growing over flow for about 16 hours. And on the right is a video of whole blood attaching to collagen. Whole blood labeled with calcine AM, so only platelets are labeled in this case, as it coagulates. Flow cells have been used by these groups for over 30 years. And the ability to have an array of flow cells, which is what the BioFlux enables, has been quite significant. And then when you couple that to maybe the past 10 to 15 years of research, which has demonstrated that shear force is necessary for both biofilm and platelet aggregation, you see that the biofilm and platelet communities were very early adopters of BioFlux. When you look at it from a perspective of global health, the leading causes of death in the world include things that are directly related to either platelets or biofilms. In the United States, heart disease still is number one. However, stroke is down to number 4, which has disappointed a lot of stroke researchers. They used to put in their grants that it was the 3rd leading cause of death in the United States, and now it's the 4th. Both stroke and platelets, I'm sorry, stroke and ischemic heart disease are directly related to platelet research. Things such as diarrheal diseases, COPD, and respiratory infections all relate to biofilms and biofilm research. This is a section also from the World Health Organization showing that these trends really aren't going away. We've had a reduction in some of the instances of bacterial diseases, but things like ischemic heart disease and stroke are continuing to climb. The one thing I do want to mention at the bottom there that wasn't the previous image is that tuberculosis is also a leading cause of death in developing countries. Tuberculosis is a biofilm producer. To date, we don't have any researchers that are using the BioFlux for tuberculosis, but we plan that 2014 will be the year that researchers will be adapting the BioFlux. One of the issues with using tuberculosis is that it's such a pathogenic organism that an instrument needs to be dedicated to a BSL-3 facility. I'm going to briefly talk about shear stress and critical parameter control. Shear stress, ranges from sub 0.1 dyne ranges all the way up to greater than 200 in pathological conditions. Any type of cell that is in the vasculature is exposed to shear stress. And this is significant in terms of trying to, when you're modeling your cell-based assays, to have accurate responses of cell morphology, gene expression, and cell signaling. Some of the positive things from shear stress include differentiation of stem cells. And some of the negative things, increased or higher levels of shear stress signal the activation of the platelet aggregation cascade. Shear stress needs to be controlled in experiments relating to vascular biology and cardiovascular disease, developmental biology, oncology, inflammation where things are exposed to some sort of shear flow, such as leukocytes going through circulation, microbiology, and microbiology also with the application of just a continuum flow. If you just take shear out of the equation of just having a continuum fusion system. And when you look at that and you compare it to static weld plates, they don't have the ability to control this critical value, which is now becoming more and more important in terms of research. This is a great example of where shear stress has a role. The endothelial cells are in the vasculature are constantly exposed to shear stress. And if you look at the image on the left, you see cells that would normally be growing under a static weld condition. This is something that you would typically see in a tissue culture plate. On the right-hand side are the same cells, but that have been exposed to 2 dynes of shear flow for 16 hours. And in addition to the morphological changes that you see, and if you've seen them for actin, there are several other factors that come into place here, which include transcriptional and translational responses, integrin responses, things like bone morphogenic protein that begins to activate as a result of this. And this movement started around 2000. There were a few papers before that, but the idea of needing shear stress in order to have a relevant assay took hold towards the early 2000s. The stability of biological conditions. One of the things that is essential for a cell-based assay is the ability to control the biological environmental conditions that lead to your integrity in the process. Other critical things that the BioFlux helps to control for, so not just shear flow, but the ability to do, for example, carbon dioxide integration if you want to do sustained tissue culture, where you would have we have the ability to control what we call environmental control of the gases that are pushed out. We can even do things such as hypoxic conditions if you want to model hypoxic systems. Something called pulsatile flow, which mimics the circulation where perfusion is pulsing, and then chemotoxic conditions where the parallel flow plates become critical. The BioFlux provides these necessary and relevant controls, including shear, temperature, atmosphere, and controlled compartmentalization of individual channels, so that you have an array of flow cells that are working all independently of each other. The BioFlux system integrates the ease of use and the throughput of the well plate assay with biological relevance of flow experiment, and it applies to the constant shear stress that closely simulates physiological conditions. And with the BioFlux system, you can easily run up to 96 assays at a time. There's simple setup, and there's no need for sterilization like you will with a traditional flow cell. All of the fluidics are kept within a plate. And so as far as maintenance for the machine, that's quite minimal, because the moment that you put fluid into a machine, you wind up having problems. But if you just have pneumatic control over an instrument, then and all the microfluidics themselves are kept within a chip, you eliminate a lot of these issues and artifacts that may come in the future. Another significant advantage to this is cost-effective use of media and cells. That the amount of cells that are required, the amount of drug and liquids, because we're working with microfluidics, all of the required materials are significantly reduced. In some cases where you're using inexpensive media such as LB or DMM, that's not so much a critical issue. But if you're using things that are more expensive, like Nature-Gel, this does have a significant value add. Or if you're doing things like BioFlux, where you have a media concern, where, for example, if you're growing bacteria with saliva and you would like to run a plate, running a traditional flow cell with saliva would require about 500 milliliters, which would have someone with a beaker and a signed consent form going around all of NIH having to spit into a tube. In this case, you really only need 2 or 3 milliliters to run the entire experiment. So the key components of the BioFlux system are the pneumatic controller, which provides pressure onto the fluidics. So the tubes that come out of the system are just for air. They're not for for flowing liquids. The well plate microfluidics, which I'll explain later, this is the consumable. It's a pre-sterilized by ethylene oxide microfluidic plate, which allows for a consistent and reproducible flow cell every time. Integrated microscope automation, that ties into our 1000 system, which is the automated system. However, that's also possible with pre-existing customers that have automated systems. And data acquisition and analysis software. The basic BioFlux system has image acquisition and analysis software with it. The 1000 system has a complete suite of high throughput, high content imaging analysis components, which I'll talk about later. To explain a little better about well plate microfluidics, this is an image of the BioFlux plate that's flipped upside down. It's in the SBS plate format, so using that 86 well plate holder will be able to hold this onto a microscope. What's required for this, for the BioFlux itself, is a inverted microscope with a condenser that has a long working distance. On the right side, you can see the essentially the wells themselves serve as reservoirs. But the biological interactions and the processes that take place actually occur within the microchannels themselves in the PDMS that's between the plate and the glass cover slip. This helps better illustrate the point that the plate here is on the bottom, where you have your wells on each side, an inlet and output. The PDMS, which is a rubber-like material, is used to cast the microfluidic channels, and then a airtight pressure interface is applied to the top of the system, which allows for perfusion to come from one side to the other. Air is used to perfuse the liquid. So while you have perfusion going on, the machine itself is not actually perfusing the liquid like a peristaltic pump would be, or a syringe pump. And then the microscope objective comes up from underneath. So some basics about the BioFlux plates. They're in the SBS plate format. The bottom is a single 170 micrometer cover slip, also known as a 1.5 cover glass. That's the optimal thickness of glass that's been used for microscopes for years. And if you look at adjustable microscope objectives, typically when you can rotate the collar, there's something that says 0.17 on it, and that relates to 170 micrometers. When you compare that to trying to image through for example, a thick plastic bottom plate, there's a significant difference in the ability for your image quality. The microfluidics enable for, again, reduced volumes. The channels are produced, the plates themselves are produced in a clean room, which allows for extremely reproducible and accurate manufacturing. And the innovative format allows for experiments to be run simultaneously without additional pumps. And unlike some peristaltic systems where you would have either 4 or 5 lines, or you would have several pumps running at one time in several experiments, that's not required in this system. And because of the different formats that we have, we're able to run a wide variety of applications. And the 48 well plate, which is the simplest to understand, includes one inlet and one outlet. This plate can be used for either low shear ranges in 0 to 20 dyne range, or high shear ranges 0 to 200 dynes. High shear is more critical for things such as plate aggregation, especially when you're looking at animal models such as mice, where you would want to do 103 dynes pressure to model thrombosis. But what this presentation is about is the 24-well plate, and the ability to have 2 inlets and 1 output. The 24-well plate currently is in a 0 to 29 format. We are looking at and in the process of designing a higher shear plate where we could do 24-well, the 24-well format in a high shear format instead of the low shear format. Because of the way this operates, there's actually 8 experimental channels. There's 4 on each side. There are 2 inputs and 1 output. Each input has about 3.5 milliliters of volume that you can put into them. And this enables for a rapid switching between compounds, adding wash buffers to conditions, or parallel flow. And actually, the way the plate looks is that you've got 2 sets of these. This is the left side plate, and on the right, you've got the same schematic, where all of your imaging is done in one location. So if you have the right low magnification imaging, such as I believe a 4X will do it, you can see all 4 channels at one time. So advantages of the 24-well plate format include chemotaxis, cell invasion, live dead staining, with 1 treatment, 1 control per cell, per flow cell, I'm sorry. Larger volumes, this becomes critical for things like biofilms that take long periods of time to grow. For example, I grew an environmental biofilm a couple of months ago out of the bay, and it took 5 days for the bacteria to grow in such a nutrient depleted medium. And then another example are endothelial cells, where you want to grow them at high shear stress for long periods of time. In that case, larger volumes enable that to happen. And more recently, the ability to mix compounds. So traditionally, the 24-well plates were used for laminar flow. We are working on it and already have some preliminary data to show that you can mix compounds in order to provide a dynamic and even more complex system for doing your live cell assays. And would like to introduce the new innovation plates. These have been out for a little while. However, we're launching them as really these were designed for the purpose of a better organized system to apply gels and other hard to work with materials. And I'll show you examples of where these come into play. The general characteristics of flow and how the BioFlux system does is laminar flow is the concept that there's really no mixing or fluid particles travel smoothly in regular paths through a continuous region, meaning that with proper engineering, you don't have the type of variability that you would with, for example, a peristaltic pump that is pumping and then, it goes through cycles and you've got these aberrations. The design behind the BioFlux was for a more continuous, more accurate system. Understanding the 24-well plate system a little bit better, we have here there's 2 inputs that come together at a junction that allow for the media to run either from input A, input B, or simultaneously. And when done simultaneously, you have parallel flow, meaning laminar parallel flow where solutions do not mix. This is a sort of graphic that shows where the 2 inlets would come together and then how they diffuse out the outlet. On the top here, you see this, I'm sorry, on the bottom image, on this top bar, the blue line is a fluorescent dye, and the yellow line is a clear liquid. And as you continue to perfuse in a higher gradient, you are able to push out the green line is the increasing concentration of fluorescence that you can very smoothly and evenly transition out one liquid to another from the two inputs. This video helps explain that.
Some BioFlux plates have an additional input well, which allows a second reagent to be introduced, such as a washing buffer, media, or drug compound. These two sources can be dynamically switched to allow for time-resolved addition of reagents or drug compounds. The two input channels can also be added simultaneously to enable applications such as wound healing and chemotaxis. Each experimental channel has a dedicated viewing area, which can be observed on an.
So that was a brief introduction of the 24-well plate. It was part of our advertising video, but it explains how the 24-well plate perfuses in, whether you're working with one inlet, two inlets, or two inlets at the same time. This graph here shows, and actually you're looking at a fluorescent dye. If you were taking the fluorescent dye in inlet B over a non-fluorescent dye in inlet A, and you perfused at a constant or a full rate into inlet B, you would see that the full channel would be perfused. As you increase the amount of non-fluorescent dye in channel A, you see as the trend goes down, less and less material that is fluorescent, showing that not only can we control this, but it's highly reproducible. The advantages of the 24-well invasion plates are that the parallel flow is achieved faster and smoother with better alignment of the input channels, meaning that as they come together at the same time, faster and more evenly. So this was really an engineering change. It's ideal for any dual flow assay, so anyone who's using 24-well plates, the traditional 24-well plates before, could use this just the same. And it's optimized to help researchers evenly seed hard to work with materials such as the matricel or gelatin, where you want to have an even flow of the two materials into the channel itself. The part numbers for this are, as seen below. For this standard 24-well plate, the BioFlux 200, the part number is 910009, and for the 1000 is 9100046. And if you would like to try the invasion plate, the part numbers are 9100050 and 9100051. One of the big advantages and things that we pushed heavily for is cell motility and migration. The traditional way of looking at migration chemotaxis are the Boyden chambers. And for efficiency, Boyden chambers have been an excellent tool for being able to see whether or not cells move from one side of the membrane to the other. But this doesn't really give you a full explanation of what's going on. You can observe the cell behavior and see actually how cells are responding to the chemical compound during time point and time course interactions. Boyden chambers are a terminal experiment where you only measure things at the very end. You can study the entire process using the BioFlux system, and applications for this include migration, invasion, and endothelial cell invasion or angiogenesis. Some of the applications that we've validated or have customers have validated include transmigration, angiogenesis, extravasation, homing, stem cell homing, which we have several papers that came out in 2013 on, invasion, and wound healing. In each of these processes, researchers have struggled to find ideal models and systems to be able to do this. The BioFlux, with the 24-well plate system, has enabled with each of these a unique set of characteristics to be able to perform this. Chemotaxis is the idea of cells giving off what I call happy chemicals, or happy proteins. Chemokines, of course, are a class of cytokines. The classic chemokine being, for example, MCP1, which attracts inflammatory cells to an area. So, for example, a site of injury would give off chemoattractants, and then that allows for neutrophils and other inflammatory cells, such as macrophages, to recognize these off of chemokine receptors, usually in the format of the CR and X, such as CCR5, which is classic for HIV, and then allow for migration. This is an example of HL60 cells, which are in a 24-well plate format. The flow is going from the left to the right, and on the bottom panel you have buffer, and on the right panel you have FMLP, which is a very well-defined chemoattracting agent. And you can see that the cells are migrating in that direction. And you know, it's great to have a video, and that's one of the best things about the BioFlux system is that you wind up getting several videos that you can put into your presentations, add on to papers, which increase the impact factor, but also you're able to quantify data, and that's what we've done in this case of looking at the effect of FMLP over time, doses of FMLP, and a dose response to that. And then you see here, as far as position of movement versus a control versus the increased concentrations of chemokines. This is an example of looking at patterning the plates in order to have half of a channel that has a gel in it and half of a channel that has buffer in it. This has become very useful in the process of studying invasion and migration. One of the challenges with the initial 24-well plate pattern was that when trying to flow in, for example, Matrigel, that the ability to flow the contents in at the exact same time were a little bit compromised with the previous plate architecture. And with the new invasion plates, this is not only possible, but it is very easily achieved. Just a brief overview of angiogenesis. It's the idea of sprouting off. You've got processes that come off of endothelial cells and begin to branch into neighboring tissues and provide for new vasculature. The steps of angiogenesis include, this list here, which I can briefly read off, but, the release of proteases that activate endothelial cells. Part of that's relating to shear stress. Removal or at least abruption of the basal membrane, and then a migration of endothelial cells into the area. Lumen formation of the membranes, and then fusion of the vessels, and initiation of blood flow. So we can't model all of that in the BioFlux system, but we can model the beginnings of angiogenesis with this system. And here's an example of cells that have migrated into a gel matrix using shear stress over time. The BioFlux allows you to not just get an endpoint measurement, but to see this process happening in real time under flow conditions. Cancer invasion is one of the core theories behind metastasis is that you start with a primary tumor. Primary tumor sheds cells into the vasculature, and then from the vasculature, these circulating tumor cells then attach onto the vasculature and then invade into secondary locations, allowing for metastasis to occur. This this event is quite significant in terms of being able to characterize which cells are invasive and which cells are non-invasive. Meaning that if a tumor starts shedding off cells into the vasculature, how much do we care about it and how quickly will metastasis occur? And CTCs have been validated as circulating tumor cells have been validated as a viable biomarker for determining prognostic outcome. And in the case of our IsoFlux system, we've used it as an essential research tool for looking at and evaluating patient samples that have metastatic cancer. These are still images of comparing HT1080 colon carcinoma cells to MCF7 cells. And so if you look at the top here, going from time point 0 to 15 hours, you see that the cells begin at the top and the bottom is where the gel is. And then you've got a time lapse that occurs over 15 hours, where you see that the cells, at least in the case of the colon carcinoma cells, begin to migrate in. This is a video showing HT1080 cells migrating over a 15-hour period. All of these videos are available on our website, and this webinar is also being recorded just in case these aren't loading up on your system right away. So in this case, in this type of example, this is a label-free experiment where everything's being done in bright field. It's always possible to image this in bright field, to tag this with GFT, or put something such as a cell tracker on this to be able to image these fluorescently over time, or to make cell populations. And with the BioFlux 1000 system, this would be very easy to achieve. And I want to remind you that this is not looking from the top going down. This is actually this is looking from the top going down. This is not, the cells are not at the top and the gel is not at the bottom. It's actually a side by side. So the cells are moving from the left to the right in this case. This is just comparing the invasive properties of HT1080 cells to MCF7s. Using our software is very easy to quantitate using imaging capabilities in bright field or in fluorescence. This is an image that was given to us by one of our distributors of the UK, Dr. Suraj Patel, who did an excellent job of showing the utility of the 24-well plate with live death staining. In the case of different biofilms, they form a carpet over top of flow cells. Some of them will ball up, and this doesn't really make a dual flow plate possible, but in the case of a Pseudomonas, it forms basically a carpet over top of the flow cell. And this is a backlight staining, so the green cells are alive and have a viable nuclear stain, and then the red cells are pyridium iodine, perfidia of iodine has gone inside of them. When you increase the concentration of sodium hypochlorite, you see a dramatic change. The only unfortunate thing, this could be a little bit better in focus, but you see that this is the same flow cell, the same biofilm, but you're able to see a dramatic shift between cells that are exposed to water versus cells that are exposed to sodium hypochlorite. And this type of thing was done within, just a time period to grow the bacteria and to mix the chemicals. This is something that doesn't take a large amount of optimization. Wound healing, which has been around for some time, the idea of scratching a surface and then watching it repopulate. We designed our own type of wound healing assay using the 24-well plate and the concept of, well, instead of using a scratch, we use trypsin to wipe off one side of a cellular monolayer and then evaluate cells proliferating and recovering back. So in the case here, you see the inlet has trypsin, and then the other inlet has a media. So the media inlet would not be affected, but the trypsin one would be. This is a video showing a monolayer of pubex that have been stripped off with trypsin and then repopulated over time. And when looking at this, on the left-hand side, you see how the wound healing occurs in, for example, a control setting, where the cells just gradually migrate back and then form a full confluence into the whole sample, in comparison to using EGF, epidermal growth factor, where the cells, very interestingly, sort of shift downward a little bit and then repopulate from both the bottom and the top. Both seem to regrow at the same time, but it's certainly an interesting phenomenon to look at. And then when you use things like cell growth inhibitors, this type of repopulation doesn't happen. The idea of compound mixing came up recently with a customer requesting to be able to mix certain compounds, which traditionally hasn't been done with the 24-well system, but was something we wanted to look into, and it appears that under low shear rates, you're able to get a mixing where you do a sort of a pulse between different inlets at different times in order to get a mixed system into your channel. And an example of this would be different drug treatments or for cells, or perhaps antibiotic treatments. You can see here that the fluid is mixed in the channel. The idea of using a physiological compound addition model for drug delivery, this is something that we have some preliminary data on, and we'll continue to work on this and would love to work with customers on developing an ideal system for being able to deliver drug dose responses over time. And so the way to do that is to create an auto-run program. This is a video of perfusing a drug into the channel, reducing the amount of drug itself, and in this case, it's actually just a dye, having the system cleared out, and then eventually reintroducing the compound, and then lowering down the titration rate. As you can see, there's a little bit of optimization that needs to occur on getting those image is cleaner. But when you look at the data that comes off of this, and this is just looking at densitometry data that was thresholded out, at the very beginning here, you see that there was no drug, or in this case, dye, that was added. And then you've got a full concentration of the dye being added. The dye came in neat. Or in the case of the drug came in. So an example of where this would sort of fit into place is an antibiotic that's taken once a day, where the levels decrease over time, and then the bacteria or the cells have an opportunity to recover if the drug does not stay in the system and is actually expelled and then reintroduced over a period of time. So this can be modified many different ways in order to show a compound mixing and a more physiological in vitro model of drug delivery. So key benefits for the 24-well plate include you've got up to 16 conditions that can be tested in parallel. You know, flexible plate format, higher quality data than transwell membranes, real-time measurements in situ. Because of the way that these plates are manufactured and the quality at which that they're done, the reproducibility is extremely high, and it saves time in transferring solutions and things required for transwell assays. If you look at doing a traditional Boyden chamber, it really is a lot of work, and it's a lot of effort just for one single data point. And assays can be performed label-free, as you've seen in the bright gel measurements, or they can be performed with labels such as GFP, RFP, tomato, cherry, or cell tracker, where you've got different populations of cells, and everything's done under physiological shear flow. So to summarize, the 24-well plates can create compartments under controllable shear flow with 2 inlet microfluidic channels. And the compartments can be used for liquid-liquid assays such as chemotaxis or cell migration, or liquid-solid assays such as invasion, where you've got cells that want to invade an area such as matrigel. The different configuration options for using the 24-well plate include the BioFlux 200 system that has the pneumatic controller, the heating plate, the pressure interface, and the control software, or the more advanced BioFlux 1000 system, which allows you to go between colors, go between positions, and to fully utilize the plate for the purposes of time-lapse image microscopy. So multi-wavelengths, multiple positions, and multiple time points. Conclusions. So we've got 2 webinars that are on online that utilize the 24-well plates if you're interested in looking at this further, including one titled The Biomechanical Pharmacology of Traditional Chinese Medicine. This is both in English and Chinese. And another great webinar out of McGill University looking at the quantification of cell migration using the BioFlux system. For additional information, please feel free to take a look at our website or contact us at sales@flexionbio.com. I really appreciate the opportunity to speak with you, and we'll be happy to entertain any questions that you have.